This experiment is a simple demonstration of a combustion reaction. In a combustion reaction, a hydrocarbon is burned in the presence of oxygen gas, forming carbon dioxide and water vapor. The equation for the reaction of isopropyl alcohol is 2C3H8O plus 9O2 yields 6CO2 plus 8H2O.
What to expect? The vaporized isopropyl alcohol will ignite in a combustion reaction, producing a small amount of heat, a flash of flame, and a swooshing sound.
This is the VZ reaction. There are many different ways and recipes to cause the oscillations. The only constants are bromine and an acid. In this redox reaction, the equilibrium is constantly being shifted to cause the different colors as the oxidation state of the bromine is changing. This reaction will just keep shifting and will not reach equilibrium for a long time if left alone. The actual mechanism of this reaction includes about 18 different steps. In this reaction, the silver wire is used as a catalyst.
Electrons can become excited and jump from their ground energy level up to a higher energy level when they gain energy. They then fall down to their ground state and release energy in the form of visible light. Depending on what the levels were that the electrons jumped between, different colors lights can be emitted.
Each ion is unique in the spectra it produces, and chemists use these to help identify what ions may be present in compounds. Normally the spectra are identified in a process called electron spectroscopy, but we can tell from basic observation that copper-2 ions give off a green color and lithium ions produce a red color.
So our experiment that we're going to be showing you today involves the decomposition of hydrogen peroxide, also known as H2O2. That breaks down into water, H2O, as well as oxygen gas, O2. This decomposition happens very slowly in nature, regularly, but if you put in a catalyst, you can speed it up. In the slow demonstration, we're using 3% hydrogen peroxide, which means that the concentration of the H2O2 is very low in the solution. Next, we're going to be using 30% hydrogen peroxide, which means that the concentration of the H2O2 in the solution is much higher. Therefore, there are more hydrogen peroxide particles being able to interact, meaning the reaction happens faster. One of the other things that we do in this experiment is add potassium iodide as a catalyst. That's the solution that you see us pouring into the top. The catalyst lowers the activation energy for the reaction so that it can proceed faster and quicker.
Iodine, when exposed to heat, sublimes when going from a solid to a gas. The reason this happens is because intermolecular forces, including London dispersion forces in the example of iodine. These IMFs cause individual molecules to be attracted to others around it. When heated, the kinetic energy of I2 molecules allows them to overcome these forces, allowing the substance to become a gas, and then, when the gas is exposed to the cold, it then recrystallizes.
In this experiment, the can is heated for 5 minutes and then flips so the opening is submerged. When it hits the water, it implodes, becoming flattened by the atmospheric pressure. This is because the hot air in the can, the steam, was rapidly cooled, which resulted in a dramatic decrease in pressure because of the condensation of the water vapor. It also demonstrates heat transfer from hot air and work being done on the system.